So the low-hanging fruit today is it's National Siblings Day. Okay, right? But that's to me that's a made-up holiday. And don't get me wrong, I love my sibling. I only have one. I have a sister. I already wished her happy National Siblings Day on the Facebook. Okay, but that's low-hanging fruit. So I went and found National Farm Animals Day.
So National Siblings Day is a made-up holiday.
Well, they're all made up. Oh, they're 100%. They're all made up. 100% all made up. You know what the worst one? You know what the worst made up one is? Valentine's Day. Yes. Yes.
So do you
Worst
want
one
to
ever.
your wife chocolate flowers?
No, because it's my birthday. It's about me that day. The one day all year that I get to be selfish. Okay, maybe more than that. Alright? So, we are in your note packet today. And when I warned you the other day that we're hopping around, we are hopping around today. Okay? Alright? So, we're going to start with the spiral of Archimedes. I want you to graph the spiral of Archimedes. That is on page 4. Okay? It's number 7 on page 4. I want you to graph that one. Just remember that instead of using thetas there, you got to use t's instead of thetas for that one. But if you would graph that at this point in time, it's just a kind of a cool parametric graph just to be thinking about and adjusting your window and stuff like that. So graph this with t's. So what I mean by that is I want a T there, a T there, a T there, and a T there. And then I also want you to put it in this window too. Okay? Go for it. So it should get something that looks like that. What are some issues that we're facing? What do you got, Kitty? Okay. Are you in radians or are you in degrees? That'd be what? Got to be in radian because we of the 4 pi. Multiplication symbol between the t and the cosine. Yep. Okay. Okay. Good on all? Yeah? All right. So today what we're going to be doing is we are going to be launching an object with an initial velocity and a specific launch angle from a specific height. Those 3 things, initial velocity, launch angle, and initial height, are extremely important. We need to know those 3 things in order to make the parametric equation that models the flight of our object. Okay? That's what the parametric equations will do for us now, is it will model the flight of our object. Okay? Right? So we can figure out if and where things will go. And then the nice part is from there, and then next week we're going to also do it algebraically, we can find different things about our object. For instance, we can find the maximum height of our object. We can find how long our object was in the air. We can find how far away our object landed on the ground. And we can find all of those different things. Or we can see if our object made it over a wall if we're trying to hit a home run ball. Or we can see if an object lands, like we're going to, in this next one, Tony and Sue are chucking lawn darts. Okay? So we can see if the object lands in the ring on after we launch. Okay? So we're actually back a page or 2. We're on page 3 here now. Okay? But actually, before we go to page 3, let's go, I think it's page 7 or 8, I want to say. This is in the middle of one of the pages coming up. Yeah, that one right there. There it is. 6, page 6, middle of page 6. Okay. So here is the parametric equations for an object that is launched at an initial angle of theta sub 0 degrees and an initial velocity of v sub 0 feet per second and an initial height of h sub 0. Those are the 3 things that you need to know about your object. If you know those 3 things, then you can model the path of your ball by saying that the initial angle is here, the initial velocity is here, and our initial height is just here. Boxes are all So then when we graph that parametric equation, we will see the true path of our ball, or of our object. Okay? So let's talk about Sue hucking lawn darts. Okay? So Tony and Sue are launching lawn darts 20 feet from the front edge of a circular target of radius 18 inches. Sue throws the dart directly at the target and releases it 4 feet above the ground with an initial velocity of 25 feet per second and an angle of 55 degrees. Okay? So let's talk about these. Now, I believe that green, I want to use the same color scheme. Green was my initial velocity. Okay? So my initial velocity of 25 feet per second is right here. That's my v sub 0. And right here, v sub 0. Initial launch angle was 55 degrees. That is right here, and that is right here. Those two pairs should always match. And then it said that Sue released it 4 feet above the ground, so that would be a +4 right there. Okay? So let's graph that parametric function so that we can see what's going on with it. First thing that I'm going to ask you to do is I'm going to have you change from radians on your calculator to degrees. Okay? First thing, change from radians to degrees. Because if you do it halfway through, then it'll erase it for you and it'll go back to what the one that was before. Okay? Control delete clears that one out. So then we can say here now that that was 25 cosine of 55 degrees times t. And then negative 16t squared plus 25 sine of 55 times t plus 4. Okay. Now, in this scenario, for Sue and her lawn dart, what does a t range from 0 to 6.28 mean? No. What does that t mean in this particular scenario? It's what? It's time. So it's the time of what? The time that the lawn dart's in the air, right? Okay? So is it going to be in the air 6.28 seconds? Could be. Okay, right? So do we need to adjust it at all is what I'm getting at. Yay? Nay? Yay? Okay, well, let's see what happens here when we hit enter. Okay? So we got that. Now, just so that I can see it, I'm going to bring it over here a little bit more. And then I'm going to expand on it a little bit. There we go. Okay? What was wrong with the other one? Oh, okay.
So let somebody else worry about it.
So, is the lawn dart in the air 6.28 seconds? To interpret this graph. So this is the actual, so if right here by where my cursor is, that's Sue standing there and she's throwing her lawn dart. Okay? Then that lawn dart is going up, 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 and up, coming down, 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 and down. Is it in the air for 6.28 seconds? Yay or nay? Why not? I mean, it wouldn't be on the graph. What can we see on the graph that means it wasn't in the air for that long? So down here, because it continued on down here, that means that it was in the air less than that, right? Okay, yep, exactly. Okay, because it crossed over, okay? Now, does that matter for us? Really, does it matter? No, that one's okay. We're okay with going extra time on these objects, okay? Because then we get it. However, look up here now for a second. If I went like this, is that okay for a graph? Because now I put just 1 second that it's in the air. Okay? So when she throws that lawn dart, does it just magically freeze right there in the air? No? Okay? So if this were the case, if this were the scenario, you would have to adjust that t value to go a little bit more. Okay? So for instance, you want it to cross the x-axis. So I'm going to go 4 and it crosses. Okay? So now we can build the target that Sue is aiming at. Okay? So if I start a second, come on. If I start a second one, the front edge of that target was 20 feet away, correct? Okay? So I'm going to put my horizontal distance at 20 feet. And then I'm going to just put a t value in there, and I'm going to leave it at 6.28 because it'll just build me a wall there then that's 6 feet up, so that we can see it. Okay? Okay? And when I hit enter here, there is the front edge of the ring that's on the ground. Okay? Then the back edge of the ring that's on the ground, it said that the ring was 18 inches in diameter, right? Oh, no, radius of 18 inches. So that would be 3 feet. So that would be 23 then. I would put another ring. So the question that was asked is, does Sue hit her target? Does Sue hit her target? Yay or nay? Yep, she puts it inside the ring. Okay? Because once again, here is this is the ring. This is the path of the dart. And so it lands in that ring. Okay? Okay. So we know where the ring is. Okay? Now, what we're going to be expanding on next week is we're going to answer those other questions. What is the maximum height of the lawn dart? What is the time that the lawn dart was in the air? What is the maximum distance of the lawn dart? Okay? So we'll answer all of those questions next week. Today we're just kind of getting our toes, wading into the launching an object kiddie pool. Okay? This one is on page 6 now. From the top of a building, 30 feet tall, a ball is thrown at an angle of 65 degrees with an initial velocity of 50 feet per second. We're going to make the assumption that gravity is the only thing that's acting upon it. So let's come up with our parametric equation for this particular one. What would my x of t function be? My x function be for my parametric equation. What would my y equation be? What would the y equation be? The standard one, or the template is in the middle of your page. What would the y equation be? Yep. How long do we think that ball is going to be in the air? How long will that ball be in the air? Just a guess. See if you're wrong. Because we can always adjust it. 20 seconds? So which one do you want to go with? Cut it in half? 12? 5 seconds? Okay, all right. Let's go with 5 then. Because that's important, right? And how can we determine if that number is not big enough? What do you mean it's not complete? It doesn't hit the x-axis. It's got to cross through the x-axis. That way we know the ball landed. Okay? All right? Graph this one for me now, please. So we inputted it. Come on. It's not there, so let's come up with a new window. What do we think in terms of x value? So this would be horizontal distance from the building. What are we thinking? How far out do you think that ball went? 80 feet? Okay. How high do you feel that that ball went? Started out at 30. We're launching it, right? After 1 second, it's up to at least 80, right? Because it's 50 feet per second. So 120, maybe? Yeah. Is our t value enough? Yep. Our t value was enough. Okay. Now, what we're going to get to, the downfall about parametrics on the Inspire is you can't do a lot of analyzing of the graph. Okay? It's just a downfall of it. It doesn't work. Okay? But what we can do, and I'll just show you this right now, what we can do is we can create a second page with a graph on it, and we can just take that y function, negative 16, but now instead of t, I'm going to have to go with x squared plus 50 sine of 65 times x plus 30. We can graph that function. We can graph that function, and then we can analyze that function. So I can analyze it for the maximum. So the maximum height of our ball was 62.086 feet. Okay? And that happened at a time of 1.416 seconds. Okay? I can analyze this height function for a 0, and that ball was in the air for 3.386 seconds. Then what we can do is we can take that value right there, and we can plug that into the x part of our parametric equation, and that tells us how far away the ball landed. Okay? So we'll get into more of that next week. Okay? Good times.